Alright, welcome back to learnpiezo.org. Today we're going to be starting part H, which is now we're going to try to actually use our piezoelectric, the ultrasonic transducer module that we built. And the main thing that was blocking us from using transducer, the main thing that was blocking us from using the picoscope to directly drive this ultrasonic transducer is that we can only get 2 volts, peak to peak, or 2 volts but RMS, 4 volts peak to peak, from our from our oscilloscope. And additionally, it had a very large output impedance. And what that means is that if we hook up a low impedance load, we will get very small current or power transfer. So it is a 2 volt power source, but if you try to, for example, power a 2 ohm resistor, therefore you're theoretically getting 1 amp. Well, the amperage, basically that output impedance means that the amperage is limited. So if you're going to try to leverage more amps, it's going to drop the voltage significantly, so it sort of trades off. So you won't get 1 amp over a 2 ohm resistor. You're going to get 10 millivolts over that 2 ohm resistor, which would make for maybe 20 milliamps of current going through that. So therefore, we need to integrate something a little more powerful, something that can handle a larger current drive. And this is larger current. So this is why today we're going to use an audio amplifier. The reason why we're going to use an audio amplifier is because it can work with high frequency. And it's typically used to drive speakers. And speakers are maybe 1 ohm loads or 2 ohm loads. So therefore, because the loads are so small, they're actually much smaller than a piezo, which sort of makes it for a troublesome arrangement, but it's going to be much more effective than just using the picoscope itself, as we'll see. So now I'll go into the setup. So here we have our experimental setup. I established this setup and I put it in a new, I done a different table so everything's all nice and clean. You can see everything all at once. So where does this system start? We have our picoscope here, and then this has, again, this is a 1-channel BNC, the second BNC, voltage probe for measurement, and then we have our excitation function generator. What the amplifier is going to do is going to take our signal from the function generator of the picoscope and give it more muscle, give it the ability to amplify voltage, and at the same time provide a larger current. So therefore, it's an amplifier. And we have this audio module here, which I'm going to describe in detail. So first setup, we have the picoscope. And this is mainly the function generator, which when we're talking about the driving system. Then we're going to have the audio amplifier. And then we have finally our ultrasonic cleaner. And that is housed in this this box right here. And I described how I built that earlier. So let's take a closer look at these components. We're going to take a look at this component, this one, and this one. We're going to show how you hook up all the connections. So if we actually go into the circuit part of this, we'll do that later. So basically, we have 3 channels on our oscilloscope. Our picoscope. One of them is going to be the arbitrary wave generator, which is our function generator. And then we have a measurement and measurement. Similar to what we did previously, this is going to be measuring the total voltage over the output. This will be used to measure current, but I'm going to do it a little differently here. And I'm going to explain why. You can use older methods, but depending on the resistor you have laying around and just your desire to be different, we're going to show you something different today. And I kind of like it. So the next part is we have here, which is the function generator. Nothing too complicated. So I'll just highlight that again. We have total voltage, we have current, which is going to be measured through voltage, and then we have the function generator on our third channel. Here is where things get difficult and things get tricky and things get not confusing, but you're going to have to take things apart, put things together. So this is the amplifier which I was just showing on the other screen here, and I'm using this to drive the speaker. So basically what I'm trying to drive the ultrasonic transducer. So essentially the first thing I did, I got my soldering iron and a small tweezer or wrench, and I desoldered all of these headers, or these screw connectors, and I also desoldered this audio input here. Alright, so once I desoldered all of those, so now what you would end up with is, I'll just draw a basic diagram of the board just to make it simple. You're going to have one connector with two connector, 3, 4, 5, 6, 7, 8, 9. So you're gonna have 9 empty holes. These actually are usually 2 holes each, but they connect to the same area. So you sort of have 9. You're gonna have 2 or more, 10, 11 empty holes, but these 2 are sort of connected, so it doesn't make a difference. And on the diagram, they're located here. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and again these 2 are the same. These are all, and now I'll explain how you connect them. So I got solderless, breadboard wire, whatever wire you want to use, you can use it. I connected wires. I'll show you exactly where I connected the wires. I'll use green. So I connected a wire here. I connected a wire here. I connected a wire here, and I connected a wire here, and I connected a wire here, and I connected a wire there. This area right here in this area region, this is where we need to provide this 12-volt input. So either you could use a laboratory power supply, which you can adjust to 12 volts, or you may have laying around, which I did, from an old router modem. I had a 12-volt power supply. So basically I took that power supply, the wire sort of looks like this, and it has like 2 little wires going through it, and then it has some like adapter at the end like that. You basically cut this, peel the wires out, and you use a multimeter to determine which one's positive and negative, and then you just hook up the proper positive negative here. So this, as it said, this is positive and this is negative. Alright. Through some trial and error, I found this is the input signal. So this is the power. This is the input signal, and this is the output signal. So here I found that the one on top is going to be where you need to put your negative, or your black wire coming from your function generator. So this is also, input signal is also the function generator signal. So that's negative. This should be the positive, the red one, not the ground. You could also put an isolating transformer, or you could not, and you just have to pay a little more attention to the rest of the business. Now we have the output signal. The output signal, as it mentions here, this is positive, this is negative. And I think that's what I have too. So you have to keep, so this should go to the positive side. And this is actually very important when you're working with your voltage probes, that you have to get the ground side of the voltage probe all the time on the ground side. Therefore, you need to pay attention to polarity, otherwise you may not have to. But generally you should pay attention, and even more attention when you're hooking probes up that are not floating probes. So here we have it. So this goes to positive, this is negative. Obviously it's going to be alternating voltage, and when you reference this one to that. And what does it look like in the final product? It looks like this. when you actually hook up the power, the LED turns on. And I think I already mentioned that I got the this is the model of function of amplifier I got, and I bought it from Amazon, and you can purchase it there too. There are other ones available all over the net. You can make your own. You can see there are not many components. I decided just to buy it. It's a nice thing. And here's this knob, which you're gonna have to play with later. So here we have it. Basically, I had a plastic box, so I just basically drilled holes through the plastic box. So looped the wires around. Just made my life a little easier. So I just drilled holes here, 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 and on the side, on the top. So I just looped it through. Sort of provided some level of strain relief because, as you can see, these are solderless breadboard wires. These are breadboard wires, so they have plastic at the end, and they have a header, and so they're just easier just to route through something. But they're convenient otherwise. Okay, and here's that knob again. I'm going to mention how we're going to adapt and use that. Here's the output of the amplifier. See, the amplifier is actually down there. So this is those two wires that you're looking at before. These two wires, you see the two wires right there coming out. These two wires are coming out right here too. So right now we just went from our picoscope, that's the highlighter, and then we're going to the amplifier, and then we're gonna finish here with our transducer. So this looks like a mess, and it is, but not that big of a mess. It could be worse. So we have our positive wire, and unfortunately, I mixed up the negative and positive. I think I mentioned that. So this is actually, this should be red, technically, and this should be black. Technically, this should be the opposite side. So I'm just going to draw that in, actually. That kind of works out well. Okay. Now that we've distinguished the proper colors of wires, let's go through and follow the... Okay, so we have this positive wire going in, and it goes into here. And these are thumbtacks. I solder the thumbtacks on to the end of each one of the wires going in and out of the audio amplifier. Just made it easier to grip on, I think, a bit better. These are thumbtacks. You basically have to sand the top of the thumbtack to give it some to erode some of the protective coating which is on it, and then you can easily solder onto it. It makes a nice area to grip for the alligator clips that come with the ground, and also from the BNC to alligator. So we hook up our first voltage probe, you know, the one that's going to measure the total voltage, and we obviously hook the other side down to the end of the output wire. So the output wire comes in. Here's a transformer. I picked up, no, sorry, it's not a transformer. Here is an inductor. So it's basically, it's like a metal circle, and it has all of these wires wrapped around it. And it has one wire sticking out there, which forms a great inductor. I picked it up from, I forget which, you know, you can probably go through your old electronics, break them open, screw them open, and then try to find these different components. I found one here, and I'm going to describe, and basically what happens is that I routed the wire, the ground wire, the wire that's coming out of the transducer, I routed it through this inductor, which then creates current, you know, through the electromagnetic field and whatnot. It creates current through the external loop here. So then I use the second probe. Instead of using, you know, as you can remember before, I used Ohm's law. Now we're using, you know, voltage, you know, current, you know, magnetic field, and then it creates voltage here. So we're actually measuring this voltage across these two terminals using that second channel of the oscilloscope to get current. So this voltage is directly proportional to the current which is passing through the inductor, and which makes for a very non-invasive way to measure current. It also doesn't consume much power. Resistors are pure power hungry devices which drop, you know, voltage significantly depending on what value you use, or you're going to get a really small signal. Here I got a really good signal, and I'll describe actually how I measured the conversion ratio, because this wasn't a standard you know, factory device. I just took it off another component. And you can use a resistor here, but make sure you use like a 1 ohm resistor or less for this experiment. You can use a resistor. But I decided again to use this one. So I will actually elaborate now on the circuit diagram just to show you what's going on. So we have our function generator, the oscilloscope, and I'm just going to draw that like that. And that has a ground because the laptop's attached to ground. So that goes on to the audio amplifier. And this, obviously, the audio amplifier also has its roots at the ground, which is the other BNC cable. Audio amplifier, or AA. Two terminals come out of there. Since it's not necessarily connected to ground, but it sort of is. I haven't tested whether those grounds are the same or whether there's some level of isolation, what amount of isolation there is. But anyways, so to power this, you're going to have plus 12 and 0 volts. So you have to actually supply the voltage. So that's a power supply. There should be some power supply here, providing that voltage to the audio amplifier. Changing colors. We will then provide, this will be the positive side, this will be the sort of the pseudo negative side. We will then head over to the crystal, which I'll draw like that. So we have the power going to the crystal, then it should be going all the way back around. We have, and I'll draw with stars. So let's say the green star is channel 1 of the function of the generator, and let's say the blue star is channel 2. So the green star here is being measured. We're measuring it here and here. So this is the positive side of the green star. This is the negative or the ground alligator clip of the channel 1 voltage probe. I mentioned that we are now measuring the current through an inductor, so we have some type of inductor thing there, and we're going to be measuring the voltage over that over that inductor. It's sort of circular. It's more like a circle like that, but we're going to be measuring channel 2 here, and it doesn't matter where you put positive and negative actually. The voltage generated over this component will be much smaller than that, always much smaller than that over the final voltage. So here we have this entire diagram. Now we have a choice here, and we don't necessarily have to measure our piezoelectric crystal. So I'm just going to actually copy this slide and paste it. So this was the measurement. This was the measurement setup. This was the entire measurement setup. However, delete that line. However, you can test anything anything using this. Let's put that there. Okay, like that. You can test anything. So if we wanted to, we could just erase. Oops, that's not good. Let's get our eraser. And we could have put it in a resistor and then call it 325 ohms, or we don't even need to use that resistor. We could just even erase this. So the first step is this, that we're just measuring the open circuit voltage. What voltage does the audio amplifier generate when we put in 2 volts input? Here it is. This is what we call the open circuit gain. So we put in 2 volts. And as you can see, we got 3.7 times 0.75 times 2 volts out from the terminals of the audio amplifier. So we have a significant gain, almost a 4. So we got around 8 volts RMS. We're going to be jumping very soon to the picoscope, and just to understand what is going on, what to expect with the signals which are coming. Next, I hooked up a 33 ohm resistor. Oh yeah, frequency. So this is the gain on the the y-axis, and on the x-axis we have frequency. So we went from around 0 hertz, and these are kilohertz. So we went all the way up to 100 kilohertz, and obviously this is this is 40 kilohertz is about the area we're going to be operating on. We have a gain about 3.65 in the open circuit area. 5 gain at 40 kilohertz open. Now practically we're going to have a load, and this changes the dynamics of the circuit. So when we have a 33 ohm resistor attached, so here now we would have a 33 ohm resistor, and I basically have 325 ohm resistors in my laboratory. I just bundled them up together in parallel, and I made a 33.3 ohm resistor. And this is what I got here. It dropped the gain, right, but not so much. We still have a gain of about 3.35 versus what, 3.65. So we still have significant increase, much more than we did with our picoscope originally, and plus we're going to have a lot more current capability. So that was 3.35 gain with 2 volts input at 40 kilohertz, and is over 33 ohm load. Okay, good. Now we're going to take a look at one last thing before we jump to the picoscope, and that is, I mentioned I hooked up an inductor to measure the current. So this is always going to be a voltage between these if you have a a live current going through. And how do you determine the current to voltage ratio? Because we're going to be measuring voltage, we're getting current from a different system, the wire that's going through. How do we do that? So I just did a simple experiment, and that would be around 40 kilohertz, which is the important frequency for us. I excited the transducer, or I excited that 33 ohm resistor. Let me undo that. So that's 33 ohms, and I measured a voltage of 6.3. I know the resistor is 33 ohms, and the voltage over the inductor, now this voltage over the inductor is this much. I can measure all of that. So it's 127 millivolts, and this is all in volts. This is volts. Because V equals IR, so V divided by R equals the current. So I knew the current was 0.2 amps, or 200 milliamps, and relating this inductor voltage versus the current, we got a ratio of 1.5, almost exactly. So basically we can multiply 1.5 times the inductor voltage, I'll write IV just to make it simple, and that would actually be the current. So if you got an inductor voltage of 0.3, you would actually have a current of 0.45 amps. Okay, so I basically just did some math and did some calibration based on this test right here. Looked up voltage and current. You're able to come up with a good number. Now we're going to jump to the picoscope for a practical demonstration.